Hey everyone, when you think about science, you probably think about the big discoveries, right? But today, we're not looking at a discovery, we're looking at the recipe behind every single one of them. There's a strict, logical formula that makes an explanation truly scientific, and we're going to break it down.
So let's start with the big question. What actually makes an explanation scientific? Now, I think for most of us, our gut instinct is to say it's about finding a cause for an effect. This happened, so that happened. But that's really just scratching the surface. The real engine of science is something way more precise, way more structured, and honestly, way more powerful.
And this is the crucial shift in how we need to think. Science basically swaps out that vague, fuzzy idea of cause and effect for a rock-solid logical argument. It sets up these things called premises, and from them, it deduces a conclusion that has to be true if the premises are true. It's not just telling a good story, it's building a logical proof.
Okay, so if a scientific explanation is a logical recipe, what's our first big ingredient? Well, it's something called a universal law. The best way to think about these is as the absolute non-negotiable rules of the game for how the entire universe operates.
A universal law is a massive, bold claim. It isn't just about what happens here on Earth or what happened yesterday. It's a statement about how things work everywhere in the universe for all of time. Think of something huge, like the law of gravity. That's a universal law.
Now here's where it gets really interesting, and maybe a little counterintuitive. Even though these laws are supposed to apply everywhere and always, you can never actually prove one is 100% true. Why not? Well, think about it. You can't possibly test something in every corner of the universe for all of eternity. It's impossible. You can't just prove a universal law by observing stuff.
So the power of a scientific law doesn't really come from what it allows, but from what it forbids. A strong law is one that draws a line in the sand and says, this can never happen. For example, the law of conservation of energy flat out prohibits creating energy from nothing. By ruling things out, these laws give us incredible predictive power.
But look, a universal law all by itself is just an abstract rule. To make it useful, to actually do anything with it, we need our second key ingredient, the initial conditions. These are the specific, on-the-ground facts of a particular situation.
Initial conditions are all the nitty-gritty details. They're what we call singular statements, meaning they apply to one and only one specific event. This is actually what we often mistake for the entire cause, the specific domino that got knocked over right before the event we're trying to explain.
So what makes them so specific? Well, they deal with a single event. They use precise details like names or specific places and times. So it's not a car, it's this Ford Focus at the corner of Main and Elm at 3:15 p.m. These are the facts that take a huge general law and pin it down to one concrete moment in reality.
All right, we've got our ingredients on the counter, our big, sweeping, universal laws, and our super specific initial conditions. Now it's time to actually follow the recipe and put them together using the power of logical deduction.
And here's the formula in all its glory. You take a general rule, you add a specific fact, and from those two premises, a singular prediction logically follows. It's not a maybe, it's not a probably. If your inputs are correct, the conclusion is a logical certainty.
I know this all might feel a little abstract, so let's make it really concrete with a super simple example. Let's just ask the question, why did this specific piece of thread just snap?
Okay, let's break it down. Step 1, the universal law. Any thread loaded beyond its tensile strength will break. Simple enough. Step 2, the initial conditions. We know this specific thread has a strength of 1 pound, and we know the weight we put on it was 2 pounds. So you combine the law with the conditions, and the conclusion is completely unavoidable. This thread had to break. That right there is a scientific explanation.
So why get so hung up on this strict logical structure? Why does it matter so much? Because this isn't just for explaining things after they've already happened. This logical recipe is the very engine that drives all of scientific testing and discovery.
To see its real power, let's level up our example. Let's forget about the thread for a minute and think about predicting the flight path of something a little more dynamic, like a model rocket. So let's apply our recipe here. Our universal laws are things like gravity and Newton's laws of motion. Our initial conditions are all the specifics. The rocket's mass is 500 grams, the launch angle is 85 degrees, we're using a certain type of fuel. When you plug all those specific conditions into those universal laws, you can deduce a very, very specific prediction.
This rocket will reach an altitude of exactly 150 meters.
And this is the absolute key. That prediction, 150 meters, it's not just an explanation for what happened after the fact. It's a testable hypothesis. It's how we find out if our theories about gravity and motion are any good in the first place. We go out, we launch the rocket, and we see if it hits 150 meters.
You see, science relies on deduction, going from a general theory down to a specific testable prediction because it's logically valid. The opposite, which is called induction, is logically flawed. Induction is like seeing 1,000 white swans and then declaring, all swans are white. It seems to make sense, but it's not a valid argument. Why? Because all it takes is one single black swan to come along and prove your general theory completely wrong. Science is all about actively looking for that black swan.
And this brings us to the immense power of falsification. A scientist proposes a new theory. From it, they logically deduce a prediction. Then they run the experiment. If the rocket doesn't reach 150 meters, if the prediction is false, then they know with logical certainty that there's something wrong with the original theory. The theory has been falsified. And this isn't a failure. This is how science self-corrects and makes real progress.
So what's the big takeaway from all this? A truly scientific explanation is not just a plausible story about cause and effect. It's a rigorous, structured, logical argument where the conclusion is literally forced to follow from the premises.
And that leaves us with a final, fascinating question to think about. If this entire process is built on falsification, on trying to prove our best theories wrong, what does that imply about the very idea of scientific proof? Is anything in science ever really, truly proven? That's something to chew on. Thanks for watching.